What is the period of oscillation of a pendulum? We still haven't learned anything about pendulums or oscillatory motion or anything of that kind. So what we will do is we will use something called dimensions. In physics, dimension refers to the nature of a quantity. For example, the nature of the height of a person or the distance traveled by a car is that of length. Similarly, the nature of the period of a pendulum is that of time, right? So a dimension can be measured in several different units. For example, length can be measured in kilometers, miles, meters, and so on. And a set of units, different units, can be associated with a single dimension. That's something you need to understand. Some of the more fundamental dimensions are those of mass, length, and time, represented by m, l, and t. There are others too, but these are the ones we'll be using in this problem. Now, the key idea in this solution is going to be that when you have two different quantities, they can be compared or equated only when they have the same dimensions. You can't compare 10 kilometers with 5 hours. The two quantities have different dimensions. But you can compare 10 kilometers with 5 miles. Because though the units are different, they have the same dimensions. So how is that going to be useful to us? Let's look at our setup, that of a pendulum. What we will first do is we will try to identify all those parameters which can affect the period of a pendulum. Intuitively, the more important factors seem to be those of the length of the rod, the mass of the ball, acceleration due to gravity, because that's what is going to make the motion possible, and the amplitude theta, which is the angle to which the pendulum is raised before it is released and it starts oscillating. There are other factors too which could have an effect, temperature, humidity, and so on, but we are not going to worry about them because they don't seem to be as relevant as these four that we have identified. So once we have this analysis, what we can do is we can say that the period is proportional to some power of mass times some power of length times some power of g times some power of theta. In other words, T is equal to K times this term. So what we have is two quantities which are being equated, and so from our key idea, both of them need to have the same dimensions. The dimension on the left hand side is going to be just T, right? We don't have any mass or length, so we will write it as m to the power 0 times l to the power 0 times t to the power 1. So what we are doing is we are comparing the dimensions of both the sides of the equation. For the right hand side, we have m to the power a times l to the power b. How about acceleration? Now for acceleration, you don't have to create a new dimension because acceleration can be represented in terms of length and time. Acceleration is the rate of change of speed, and speed has a dimension of l by t, distance by time, and so acceleration has a dimension of l by t square. The angle theta in radians is defined as, if you take a portion of the circle with theta at the center, then theta in radians is defined as s by r, the length of the arc divided by the radius. Both of these have a nature of length, and so the dimension of theta is 1. So such quantities we call them dimensionless quantities, and so we are not going to consider it here at all because it does not have any dimension. So substituting the dimensions here and raising them to the right power, what we get is m to the power 0 times l to the power 0 times t to the power 1 is equal to this term. And since these both represent the same dimensions, a must be equal to 0, b plus c must be equal to 0, and minus 2c must be equal to 1. Based on that, we can find the values of a, b, and c. On substituting these values in this equation, we get t equals k times square root of L by G, where k is the constant. We can find this constant by conducting a series of experiments and plugging in the right values of L and T. So what has been observed is that t equals 2 pi times square root of L by G, k equals 2 pi. This is true when the amplitude theta is small. For larger values of theta, this is no longer true. There needs to be something more added to this equation. So this kind of analysis is called dimensional analysis. And of course it has its drawbacks. In this case we got lucky in the sense that we could identify the exact set of parameters. But if you add something which is not really needed or omit something which is actually needed, you're going to get a totally wrong answer, right? Yet this kind of an analysis is useful, especially in systems which you have a fairly good idea about and for which you can identify the exact set of parameters.